Hi everyone, welcome to another video in the Advanced SQL series. This time it is going to be a little bit different of a video because it's going to be a little bit more theoretical. So we are going to go over the concepts rather than over the code. However, it's going to have many practical examples, and we are really going to go into today's topic step by step and from the very beginning. And today's topic is join algorithms. So these are not join types as in full inner, left and right. However, these are join algorithms. So how the database can connect the two tables regardless of the join type. Not entirely regardless, but how do you connect the rows from the two tables that you get your result set. And this is what we are going to discuss today. So let's get right into it. But before we get into it, what we need to discuss is a access method. And this is a simple access method. So essentially an access method is how the database accesses data that is stored on your disk. So essentially the data from your database is just saved in files on the disk. And every time you want to read the database needs to retrieve the data from the disk. And it can do so in many ways, or in several ways, maybe I should say. One of them is a full table scan access method. And this is what we need to know for this video. So basically, what we have, let's say that we have the query that we have right here. So what the database does is the database goes to the disk. On the disk, it finds the table, which is saved more or less like this. So it's not entirely saved like this. Of course, it's saved using zeros and ones. However, let's currently represent it like this. So it just goes over. It knows that it needs to read everything from this table. So the name and surname column. Therefore, it goes over here. Okay, I have a name, surname, and I go over all the pages or the rows, and I read the results, and I display them in the result set. So essentially, this is an access method where you access everything from a table. And this is an access method that if you are working with big tables, you want to avoid. You would much rather have this index scan access method. And if you have not seen a video on indexes, it should show currently on the screen. I would recommend that you go and watch it because I will be basing this video a little bit on the knowledge that was acquired by watching the video about indexes. So in today's video, we'll discuss three main algorithms, and these are algorithms that are shared by most of the most popular DBMSs. So the one that I currently think is not shared is, for example, the Mege-sort join. I don't know if MySQL supports this. I don't think they do. However, these will be the three basic join algorithms that exist. Of course, most DBMSs have their own variations, and the implementation of these algorithms will be also different for different DBMSs. This is why I will explain to you the general concept and not exactly how this is done, because this, first of all, we don't always know how exactly this is done. So I will just explain it to you based on the documentation that we have, that is basically provided by the developers. And then I will try to generalize it so that it fits most of the implementations, right? And you have to be prepared that most of the DBMSs will have like some sorts of own variations of it. And we'll also have like different algorithms that they developed and that they think are useful and are special to this DBMS. Okay, so first join algorithm is a nested loop join. So what happens if we have a nested loop join? So first off, we need to establish, so we have two tables, right? We need to establish which is our outer, also so-called driving table, and which is our inner table. Usually the smaller table, so in our case B, will be the outer driving table, smaller when it comes to number of rows. And now what happens is for every row of the outer table, so for us it will be a table B, we'll look for matches in the inner table, right? So we'll select the first row from table B, we'll go over table A, searching for an entry that fits our join criteria. We'll do an example in a second, right? And then it will return all matches to the result set. So basically, as you maybe already noticed, we'll be accessing this table A many times. This is why it's very nice if we have a highly selective index, because as you know already from the video about indexes, once again, if you have not watched it, please now go and watch the video about indexes. This will be very, very good because the access to the table A will be very quick, right? Because if we have a highly selective index, this means that a single combination of values of columns in the index returns you very little rows, best if it returns one only, and it's, for example, a primary key. So here it will be very quick if you have a highly selective index on the inner table, which in our case will be at the table A. But this is all talking. Let's currently make an example. So let's assume that we have two tables. These tables should be a little bit familiar to you if you have ever worked with Oracle sample schema called HR, right? These are basically data where, among other things, you have data about departments and data about employees, right? So employees are employed in departments that we have right here. And currently I limited the data set so that we have only 2 departments and we have only this number of employees. And let's currently analyze the following query. So we want to select the last name and department name from departments. And to this, we want to left join employees on department ID equals department ID, of course. So here we have department ID and here we have department ID. And we are left joining from departments to employees. Okay, so right now, what will be happening is departments, because it's a smaller table, will most likely be declared as the inner, so driving table. And employees, will be declared as outer table, so the driving table. And employees will be declared as the inner table because it's bigger. So what happens is we start to loop over all the rows in the departments table, right? So we select the first row right here, and we go over all the rows in the employees table, right? Let's assume that we don't have an index. So we take this one and we go one by one. So we check this one. Okay, it's not 10, right? It's the department ID here is 10 and here is not 10. The next one, not 10. Next one, not 10. Next. Until we get to Jennifer Wallen, probably. And here we can find the 10. So, okay, we have a match. We add this to the result set. And then we continue, right? We have the next row, here we have 20, we have the next row, here we have 30. Okay, we have finished. This iteration of the loop is finished. Now we go back to our departments table. We take a look at the second one. So here we have department ID 20. Okay, therefore, once again, we go to the table. And what we do is, once again, we go from the top, right? So we have 30, okay, that's not a match. 30, not a match. 20, that's a match, right? So we take this 20, we take this row, and we add it to the result set. And we continue, right? So here we have 30, no match, no match, no match, no match. 10 is no match because we are currently analyzing 20. And finally, here we have 20. So we add this 20 to the result set. And then we have 30 at the end. And we are finished because we have finished all the rows that we have here. So we had 2 iterations of the outer loop. And here we had, of course, we had to iterate over the rows also twice. This is why it's called nested loop, because you really have a nested loop. So one loop over the departments. This is the outer loop. This is why it's also called the outer table. And the inner table is where it's the inner loop. So some ORMs like to basically do this manual, where they just manually execute a number of selects to like manually recreate this nested loop join logic. And I think currently you can see why it's very important if you want to optimize a nested loop join that you create an index on this join key here, because then this lookup, instead of scanning all the rows and performing what we discussed at the very beginning, so this full table scan, which is usually pretty bad access method if you are working with big tables, it can just do it based on an index, and as a result, do it much, much quicker. So that was a nested loop join. And the nested loop join is, I think, one of the most basic join algorithms, I think, supported by most DBMSs, as I said. Now, this one that we will currently take a look at, Mege-sort join, is, as I think I discussed, or as I said at the beginning, basically, I think MySQL does not support it. And because it's a little bit controversial, right? It has maybe not so many use cases, and it has one important drawback. But let's go over the algorithm first. So first, what we need to do is we need to read full table A and full table B from disk into memory. And this is a problem because this rarely fits into memory. Or maybe I shouldn't say rarely. This needs to fit into a memory, right? This is a precondition. Then what we need to do is we need to sort the entries on the join key. So basically, if you know anything about algorithms, sorting is not the easiest thing to do. So it usually costs a lot. And essentially, of course, the database can also handle this usually if this cannot fit into memory. But then we have this, it spills into the disk. Therefore, the database has to somehow manage, okay, has to load like parts of it into memory, then do a sort, and then save it to disk, and then it becomes a very bad join algorithm to use, in my opinion. Then the other two that we are going to learn today, or one we already learned, are probably a much better fit. However, there are use cases where you can retrieve the data from the table already sorted. For example, if you have it clustered somehow, maybe on like a cluster key. So I know that DB2 would by default have like the first index that you define is like a cluster index, which means that it saves the data in a particular order. Therefore, if you can retrieve the data already sorted, then you can skip the sort part, and then it becomes a very, very interesting join algorithm. Even though, saying this, I think it's the least used out of these three. So essentially, it works best if the two tables can fit into memory and are already sorted. For example, extracted from a clustering index. Extracting from a normal index will not always work. Okay, this was theory. Now let's jump to the example. So essentially, the very same example. It starts off, we need to read all the tables from disk, which was not the case in the previous one. Second step, we need to sort them, right? So here you can see, okay, here we have it sorted. It can be just randomly because we only have 2 rows. And here you can see that the order will change, right? So that department ID 10 will jump at the beginning. And essentially what happens is now after we have sorted this, it's very straightforward for us to combine these two, right? We can start here, we can see a 10, we go right here, we can see a 10, we go to the next one, okay, we have a bigger number. So we go back here, we see a 20, and now we know that we don't need to start from this, we can start from this value, and this here we have a match, here we have a match, and here we have a bigger number. And here we see that we don't have basically a match, so we finish. And we are done, right? So very little steps necessary, right? So we take, once again, we take the 10 right here, we go over here, we see, okay, we have a 10, so we save this to the result set, we go further, we have a 20, okay, that's not a match, so we go back right here. We select the 20, we go back right here, we have like 20, 20, so we add these to the result set, then we have 30, that's not a match, we can finish because we have no more rows. So here you can see much fewer steps if you exclude the sorting, because of course the sorting is an algorithm to discuss and you can do it in many ways. And probably we could do a video on sort algorithms in DBMS or in database engines. However, this is essentially how it works. Nothing to be added. And really this, if you have bigger tables, will not really work. And what I would like to emphasize is, of course, the join result is exactly the same and will be exactly the same for all the 3 algorithms, because this is what happens sort of under the hood, right? So if you are just a basic user of the DBMS, you don't even know which algorithm the database has chosen. But about this at the very end. Now let's jump to the third join algorithm, which is a hash join. And the hash join, what it needs to do, it first sees the two tables, okay? It defines which of them is smaller, but in terms of bytes, not in terms of rows. So basically it has the size in bytes of the table. It usually will pick the smaller one. Based on the smaller table, it will create a hash table where the key is the join key. So if you don't know a hash table, so basically a hash table maps a key to a value, right? It's called a hash because you would often define the hash key with some sort of hashing algorithm. Now, if you don't know what hashing algorithm is, it's basically a function that takes an input and then gives you an output that can have different properties. It usually is the same length. And very often, for every unique input, it gives you unique output, although this is not 100% necessary. And also, like what exactly hashing functions are used, this is very often not clear. However, what's important is that we have a hash table, and the hash table is sorted on the join key. And this is important. This will be very important with our example. And now basically for all the rows from table A, we get the hash value of the join key. So we apply the same hashing function to the join key, and we go to the hash table and we check, okay, is this value there or not? If it is, then we return it as a result. So basically it works best if the hash table is small, because it needs to let this table be into memory. And of course, creating hash table also takes a little bit. Here indexing the join key will not improve the performance, but indexing an independent where condition from the query will improve it, right? So if we have an independent condition, a where condition in the join on the table A or on table B, this will work, right? Because if we can get the table B smaller before we start creating the hash table, then it will help us, right? And the independent is just that it affects only one table. And basically here you should really pay attention. So basically you always should pay attention that in your select clause, you should select only the columns that you need. I think I say this in every SQL video that I make. But here it's especially important because the time that it takes to create this hash table is dependent on the size in bytes of the table, not about in rows. Therefore, the number of columns also has an impact on this. So it's heavily decreased. If, for example, it does not fit into the memory, and once again we have this spill into the disk, and then the database needs to do some serious work, and we will not go into this. So best if it fits into memory. Once again, let's go through an example. So we start in the very same way, right? So the employees table just exists. We have the same join, and here we read this departments table from disk. Once again, it's smaller. It's probably also smaller in terms of the size in bytes because it has fewer columns, fewer rows, although precisely to depend on the data type of the column. However, we can assume that it's smaller, and we'll be defining a hash table based on the departments table. So now how a hash table would look like, it would assign some sort of key to our row, right? So here we would have the 10 administration and then some sort of hash key, and then we have 20 marketing and once again a hash key. And now, so I just assigned 1 and 2, but there are different hashing functions that define you a different result. For example, you can take like ASCII value of all the characters here, you can sum them, or not here, but in the join key, which is the 10 here, you can like sum them and then divide by a number. Essentially, there are different hashing functions. However, here I just assigned them 1 and 2. This doesn't really matter. And what's important is our hashing function that we currently created assigns 1 for 10. So for an argument 10, it produces an output 1 every time. For an argument 20, it produces an output 2 every time. And essentially now what we'll be doing is we will be going over the rows in the employees table, right? So we're starting from the first one, and we'll be looking for values in our hash table, right? So starting from the first one, we take this 30, we apply our hashing function on 30. So let's say that we will get 3, like following this pattern. And we now look for 3 in the hash table, right? And because we now know that this table is sorted, we can essentially now, we know that this is 3, so we can right away jump here. We don't have to go through all the tables because we will know that this 30 and this value 3 that will be returned by the hashing function will be on the 3rd place here in this hash table because it's sorted, right? So here it's sorted ascending. So we know that it would be here, but we jump here and we don't have it. Therefore, we exclude it, right? Very quickly. Next one, similar situation. We jump to the next one, this row, we hash this value, we get now value 2. Therefore, we jump to this hash table to the 2nd place and we see, okay, we have a match. We go right here and we can return the value marketing. Now, what if we had non-unique join key? It can happen, right? We had 2 2s here, for example. Here we would have a longer list, right? So we will have an array of values instead of just one value. So one value, I mean by 20 marketing, like one row, right? We would have like the next rectangle here. Therefore, we would need to jump here and then check in this array which of these matching values is our matching values, based not this time on the hashed, but on the real value that we have right here. But because we have only one value here, we don't have to do it, right? So we just go in here and we find a match. Right, and we found the match. Therefore, we continue. We continue here. We have the 30. We didn't find a match because there's no 3, no 3, no 3. And here we get to 10. Similar situation to 20, right? We hash 10, we get 1. Okay, so that's the first place in our hash table. We jump to the first place immediately, and we see 10 administration. Therefore, we take the last name from here, the department name from here, and we put this into our result set as we did with the marketing and by the last name in the previous slide. And then we continue, right? We continue basically here with the 20, so the 20 would also put in the result set, and we have the 30, which would not put in the result set. And this is it. We have just gone over the 3 most common join algorithms. So now I think you are ready to jump into SQL Developer or any other tool that you're using, access the explain plan, and a video about how to read explain plans is coming soon to the channel. And basically there you'll see, if you execute some kind of join, you'll probably see like either a hash join or a nested loop join or a Mege-sort join. However, now the question arises, like, how does a DBMS decide what join algorithm to go with? And the answer is simple. The answer is table statistics. Stupid, I could say. And the table statistics are numbers or are statistics that a DBMS gathers about a table. And these are basic information. The number of rows, the column, the data types it knows, but the number of unique values in the column, sometimes the distribution of the values, like max, minimum value. And it uses this information to estimate a cost. So basically the table statistics, to estimate a cost of every possibility. It calculates a big number of possibilities, big number of explain plans, and then it, based on these table statistics and on the estimated cost, it chooses the lowest one. So the algorithm with the lowest cost. And this is why it's important to keep your table statistics up to date, so you don't have to refresh them all the time. Just if you make significant changes to a table, right? Let's say you change more than 20%, I think I saw somewhere, of rows, but this is not really a rule, right? 5% can make an impact and 40% cannot make an impact. This doesn't really apply in every case, but I think it's good to have like some kind of idea in your head. So essentially, that is how the DBMS will decide what type of join algorithm to use. Okay, from my side, for today, that's everything. I hope you learned something. If you did, please leave a like button to this video. Leave also a comment with what would you like to see next, or maybe what you liked about this video, what you would like me to talk about a little bit more in the future videos. And also subscribe the channel if you want to see more videos like this. But for now, I would like to thank you all for watching, and I will see you in the next video.